We're just going to remind ourselves of the reciprocal trig functions. So we know we have sine theta, cos theta and tan theta. However, quite often in A2 maths you'll find that sine theta is on the bottom of a fraction. We'd ordinarily write this with indices, so usually we write sine squared theta like that. However, if I've got 1 over sine, I don't want to be writing sine to the minus 1 theta, to use minus 1 to represent the reciprocal, because we already use minus 1 to mean inverse of sine. So, we just invent a new function which means the same as 1 over sine theta, and we call this cosec theta. All it means is 1 over sine. Similarly, we have cos theta, which we call sec theta, and last of all, tan theta, or 1 over tan theta, 1 over cos theta, which we call cot theta. Okay, these come from ancient, old functions which we use a lot in navigation, which is why they have their own names, and they are defined geometrically if we think back to the unit circle, and you take your tangent. You can define sec and cosec on this diagram in similar ways to what we did before, using right angle triangles. We won't ever really see them like that. We can do that if you want. You can do that if you want in your own time, but for now we just need to know these definitions. Okay, so how will we use them? Well, one way is often finding new identities or proving identities. So we've got our standard identity, which is sine squared theta plus cos squared theta is the same as 1. We can divide through here by cos theta squared even, and derive a new identity. Sine squared over cos squared is tan squared theta plus 1 is the same as sec squared theta. We can do a similar thing. Divide through by sine squared theta. And derive another identity. 1 plus cot squared theta. Remember that sine over cos is tan, so cos over sine, the reciprocal of that will be the reciprocal of tan, cot. So 1 plus cot squared is the same as cosec squared theta. You'll use these identities a lot in A2 maths, especially this one. It's not that it's more useful than this one, it's just that we tend to use sec and tan more often than cot and cosec. Don't ask me why, it just seems to be an arbitrary choice that we use those more. Okay, so we've met some new identities. Finally, we'll just look at what the graphs of these functions look like. So we'll look at sec first of all. Best way to remember this graph is to first of all think about y equals cos theta. I'm going to plot this in radians just so we get used to using those. So cos theta would look something like this. Vaguely symmetrical, it's supposed to be. Between 1 and minus 1. Minimum at pi. Maximum again at 2 pi, because that's one full oscillation. That's equivalent to 360 degrees. Minus 2 pi, pi. That would be pi over 2, etc. And now we think about what would 1 over each of these values look like. Well, first of all, we'll start off with y-intercept. 1 over 1, that's just 1. So we know our graph must have a y-intercept of 1. Next thing we need to consider is what happens when I try to do 1 over 0, because cos theta is 0 here. Dividing by 0 usually gives me an asymptote. Certainly our function will be undefined there. And again, there's another 0 over here, here, and here. Okay, so what happens in between these? So we know that in this region here, cos theta is getting smaller. 1 divided by a small number, a number less than 1, gets bigger. Our graph will look something like that, going up towards an asymptote. And cos is what we call an even function. Its negative values are the same as its positive values. So the same is going to be true of 1 over cos. Our graph will be symmetrical, a kind of U shape there. Not a parabola because it's limited by these asymptotes. Okay, what happens the other side of this parabola? Well, we've got 1 divided by a number very, very close to 0, but negative. That will give us a very, very large negative number. Same here. And in between, I've got 1 over minus 1, which is minus 1. Again, I can join it up with a nice smooth curve. And we can sketch it. And then just like cos, our graph repeats. And so on. That's what our graph of sec theta will look like. I'll leave you to try and do a similar thing for cosec. Again, sketch the sine graph and then think what would 1 over that look like. We'll just do tan, although it'd be a good idea for you to pause the video here and try doing cot and tan yourself. Okay, so again, it should be vaguely symmetrical and they should be asymptotes. Usually I'd advise drawing the asymptotes first, because otherwise you get not very straight asymptotes, as I've got here. But the idea is there. Okay, so similar idea to before. Y-intercept for y equals cot theta. 1 over 0 is very, very large. 1 over 0, when I'm plugging in a negative value, or very, very close to 0, will give me a very large negative value. And then when I start dividing by bigger and bigger numbers, I'll get closer and closer to 0. When tan has an asymptote, that means I've probably tried to do a number divided by 0. So if I take the reciprocal of that, I'll have 0 on my numerator. So therefore, where tan has an asymptote, cot will pass through the x-axis, and where tan passes through the x-axis, cot will have an asymptote. So I'll probably draw in those asymptotes now. And then it's just a case of joining them up with nice smooth lines. Where have we went? So, those green lines will be the graph of cot theta, and it's easiest to draw if you sketch it over a tan theta graph. Hopefully, though, eventually you'll remember what it looks like. And that's basically all you need to know about sec, cosec, and cot.